So there's a couple different ways we can start to interact with this equilibrium constant and how we can use that value to determine a couple different things. But just a general reminder, when working with that equilibrium constant, it has to be the concentrations of your reactants and products once we've reached equilibrium. If we're going to say this is the constant when we're at equilibrium, values we use when determining that has to be our equilibrium concentrations. Additionally, we can also look to see how that concentration has been changing over time as we go from initial until the point where we reached equilibrium. That's going to introduce kind of a new bookkeeping method that we call our Rice tables. Rice tables. It's just a new way of doing math. We used to do, once upon a time, we actually taught stoichiometry just in general with this, but turns out it's a little more cumbersome than what we need at that kind of Chem 1 level. Because really, we're just in Chem 1, we're just like, okay, if we got this many grams of stuff, how many grams of product? And we're really just worried about the two pieces. We're not worried about everything. Unfortunately, or fortunately, depending on how you look at it, when we are solving for equilibrium, we have to take into account all of the concentrations, all the reactants, all the products. It all gets lumped together. And so we got to keep them all straight and have some way to kind of organize and navigate our mathematical values. So that brings us to our RICE tables. RICE is just an acronym that stands for reaction, initial concentration, change in concentration, and your equilibrium concentrations. And it's just kind of a tool for organizing the numbers, keeping track of the math so we can see what it is we've got, what we started with, and then how we can solve for our equilibrium constant. Cool. So let me show you an example. Let's look at how we can start to navigate one of these. So here is an example for us. This is going to feel pretty math heavy because really that's where we're at, but it's going to be a nice way to kind of organize our data and think about what it is we're working with. So let me real quick throw the final reaction up here, and then we can kind of look at what information we have. So we've got 2 moles of our NaCl being added to a 1 liter flask. Oh, tricky, tricky, tricky. That is not molarity, but number 2 moles divided by 1 is going to be 2 molar. Nice. At equilibrium, we know that the concentration of nitrogen monoxide is found to be 0.66 moles per liter, which is molarity. And then it asks, what is the value of K? Well, it doesn't feel like it, but we actually have enough information here. So this would be our reaction. We need our initial concentrations, our change, and then our equilibrium. I'm going to draw another line here for our equilibrium portion. Cool, so let's just plug in what we know. We know we started with initially 2.00 molar of our reactant. And at the beginning of the reaction, well, we don't have any products. We can, unless we're told otherwise, there's very few instances. It can happen, but pretty far and few between for most systems. Usually we don't start with any of our products for our gaseous species. You can assume that the chamber is empty with the exception of our reactant. And then we know that after everything is said and done, the equilibrium concentration for our nitrogen monoxide was 0.66 molar. And that's all we know. Well, I guess we could also write our K value. We know that Kc is going to equal our products, in this case, our NO concentration squared times our Cl2 all over our reactants, which was NaCl quantity squared. But remember, in order to use this equation, we need our equilibrium values. We got to finish our Rice table. Well, good news. We know how much one of them changed. If we started with zero molar of our nitrogen monoxide, we know that it has increased by 0.66 molar. We know that's how much it's gone up. And good news, the extent of our reaction here is going to be based upon our stoichiometry, based upon our mole ratios. Because we know that for our nitrogen monoxide, in order to form that, it's got to come from the NaCl. And it's a 2-to-2 ratio, which is the same as 1-to-1. So if our nitrogen monoxide is increasing by 0.66, our reactant would be decreasing by our 0.66 molar. And if we look at our last two here, we know it's a 2-to-1. It is half as much. So if this is a 0.66, this would be 0.33. It would be increasing at a rate of half as much. Cool. So we can add it down. We know we're going to have 0.33 of our chlorine, and we're going to have 2 minus 0.66, 1.34 molar of our final reactants. Cool. Now we have our equilibrium values. Oh, awesome. So now we actually take these numbers and plug those into this Kc formula. And then I think we're back to math. Let me erase here a little bit so we got some room. I'm going to leave my equilibrium values up. Ooh, that's satisfying. Cool. So let's plug in our numbers real quick. So we're trying to solve for the KC. We know our NO was 0.66 quantity squared. That's going to be times 0.33 all over our our NOCl concentration, which was 1.34 quantity squared. We can solve. That's just a math number. You can solve and get an answer. Yeah, what do you get there? I'm plugging it in real quick. We've got 0.66 power squared equals that times 0.33 divided by our 1.34 raised to the second power. And you end up with 0.080 with two significant figures, 0.080. Final answer. Reminder, KC is unitless. And so here's our final answer. This number, much, much less than 1. If K is products over reactants, and we have a number less than 1, that means we have more reactants than products. As a result, we would say that this is a reactant-favored reaction. And that was true. Look at your concentrations. You had way more of your starting reactant than you did of your final products. Makes sense that our K would be a value less than 1. So that's the chemistry piece. Most of this is going to be math. We're just kind of coming back and look at that chemistry part. Cool. Let's look at another example here real quick. Another example. Nope, don't want that. Cool. So let's say you knew the K. Oh, now we know the K. And we've got some starting amounts of our different pieces. Now the question is, could we figure out what those equilibrium concentrations were? Well, I think we can do it. Let's set up our ice table here so we can keep track of everything. We got H2 plus I2 going to our 2HI. Again, as a general reminder, to try to get your formula, it's nice to know what it is you're solving for. We're going to have our HI concentration at equilibrium squared. That's going to be all over our H2 times our I2. Cool. There's our KC expression. Now we can start looking at some of the numbers we got. Well, 1 mole divided by 1 liter. Well, that's 1 molar. So we know here's our reaction. Our initial concentration, we got 1.00 molar of this, 1.00 molar of this. And unless told otherwise, we can assume we don't have any of that product. Whoa. Hey, stop that. Sorry, I'm trying to zoom in a little bit. Cool. I think that's all we know. Oh, no, we know one other thing. We know the KC. We know what all this stuff is going to be equal to, that 5.33. Okay. Well, now we're out of information. We don't know how much it's changing by, but we know it is proportional. So for example, in math, if you don't know something, you put in an X. We're going to say that this hydrogen goes down by some amount. We don't know what it is, so we'll call it X. But we do know it's a 1-to-1 ratio. So if this is going down by X, so too would our iodine. And for every X that gets used up on the left, we end up making 2X worth of product. So if we solve it on down, we're going to have 1.00 minus X for our hydrogen when all is said and done, 1.00 minus X for our iodine, and we're going to have 2X for our hydroiodic acid here. Oh, cool. Sorry, I'm kind of squeezing it in here, but I think we can actually plug in then and solve for a variable. We knew that KC was 55.3. That's going to be equal to our HI concentration. Sorry, my wrist is catching here. HI concentration squared, which was our 2X at equilibrium. And we're going to have 1.00 minus X times 1.00 minus X in the denominator. Well, good news. This binomial times itself is the same as saying that quantity squared, which makes the math really nice here, because I think we can square root both sides and simplify our work here. So these squares are going to cancel. Square root of 55, square root of 55, square root of 55.3 comes out to 7.436. And that's going to equal our 2X all over 1.00 minus X. I can distribute up this 1.00 minus X. Let me erase here a little bit to give myself a little bit more room. I think I'm officially out of space. Let me erase here. Cool. I can multiply up. Number times 1 is just that number. So we've got pencil, 7.436 times a negative x is negative that number x. That's all equal to 2x. Now we can combine like terms. We're going to add over that 7.436x. So we got 7.436 is going to equal 9.436x when we combine. And then we can divide everything by 9.436 to get x by itself. I'm filling in real quick here. 7.436 divided by 9.436. And we get 0.788. 3 sig figs. I believe. 0.08. Nope, it was a 7. 788. We're not quite there yet, because what was x? X was the change in the concentrations. Well, now we can go ahead and solve. We've got our x and our x down below, so we're going to have 1.00 minus x. Well, in this case, it's going to be 1.00 minus, so 1 minus our answer. That's going to come out to 2.11 decimal places when we're looking at our addition or subtraction. So that's going to come out to our 0.21 molar for both our H, hydrogen, and iodine here. We would take our 0.788 times 2 to solve for our product. In this case, it's going to be 1.57, 3 sig figs, so 8 molar for our HI at equilibrium. So mathematically, it looks like we got way more products than we had reactants, and that makes sense. That makes sense. Our K was really big. It means we should have way more products than we do have reactants when all is said and done. Cool, just a couple examples of how we can start to kind of keep track of these numbers. The math is pretty straightforward. We just have to make sure we're following along with what we've got in terms of our digits for our different calculations. Feel free to shoot me questions if you're having questions as you're working. Hopefully this is enough to get you going on some of these types of calculations.